So here we are in Unit 6, Energy Resources and Consumption. When we look at this unit, it's chapters 19, 20, and 21. Chapter 19 deals with fossil fuels. Chapter 20 deals with conventional alternatives to fossil fuels. And chapter 21 is new alternatives to fossil fuels. So you kind of get a history of energy resources and consumption. So let's talk about what we've been using for a really long time, fossil fuels. So we're going to look at energy sources that we use. We're going to look at this idea of EROI, how we get fossil fuels, how they form, how we process and use them, how we're going to take a look at the conventional oil supplies, how we are extending our reach for those fossil fuels. We're going to look at the environmental impacts of fossil fuel use and ways to minimize those impacts. We're going to look at political, social, and economic aspects of fossil fuel use. And we're going to look at ways to conserve energy and increase energy efficiency. So here's our case study. Alberta's oil sands and the Keystone XL pipeline. When I was in college, it was probably 1995, so you're talking quite a while ago, I took a clastic sedimentology class as part of my geology major, and my professor stood there telling us about these tar sands or oil sands in Alberta and how they were not economically feasible to help to access to use as oil, and we didn't have the technology because oil was still too cheap. But here we are, 30 years later, and we are getting oil from these tar sands. So what are tar sands? It's an oil sand or a tar sand. It's sand and clay combined with this tarry type of petroleum called bitumen. So it's like a slime, slurry goop of sand and clay with this bitumen in it. And they're around all over Alberta, the province in Canada. So in order to get at them, you have to strip mine, clear the forest, and strip mine the land. So pull the land off the top, mix those deposits as they quarry them out with hot water and chemicals to separate the bitumen from the sand, and store that wastewater in toxic tailing lakes, open lakes of toxic leftovers. All right. Until oil prices really started to rise in 2003, getting at these deposits was not profitable. They would lose money on it. But after oil prices started to go up tremendously in 2003, it became profitable. And we in the United States are one of the biggest buyers of tar sands oil. So in order to get the oil from the fields in Alberta, the U.S. and TransCanada built this Keystone pipeline. Okay, so the existing pipeline is this purple line. All right, it goes down into Texas and Louisiana and over into Missouri and Illinois. Okay, they had proposed extending an extension of the pipeline to shorten the distance, to increase capacity, and to basically allow oil fields in North Dakota and Montana to contribute to that oil flow. But it's near the Ogallala Aquifer. Protests started as a result when they proposed it because the Sandhills area of Nebraska is ecologically sensitive, and the presence of this pipeline over the Ogallala Aquifer, which we have already talked about. We really, a lot of people think we really shouldn't be investing in oil, and we should spend the money that we would be using on this pipeline to transition to renewables. And in 2015, Obama did not approve the pipeline, so that's where we currently are with it. So as a species, we have devised a whole lot of ways to harness both renewable and non-renewable forms of energy on the planet. So in this chapter, we're going to talk about coal, oil, and natural gas. In the next, we're going to talk about nuclear, biomass, and hydropower. And in chapter 21, we're going to talk about solar, wind, geothermal, and briefly talk about tidal. So our conventional energy resources are non-renewable. Nuclear is a conventional alternative that is also non-renewable, but the rest of these are renewable. So most of the energy comes from sun, which drives winds, the water cycle, and photosynthesis. When we have plants that die and other organisms that die, and they're buried under sediment, under the right conditions, their carbon can turn into fossil fuels, okay, such as coal, oil, and natural gas. All right. There are other ways to utilize energy, like geothermal energy from the Earth's core, the heat of the inside of the Earth, and the bonds between protons and neutrons in atoms, and that's nuclear energy. When we have resources like sunlight and geothermal and tidal energy, they are perpetually renewable. We're never going to run out because the tides are always going to be doing their thing. Coal, oil, and natural gas are non-renewable because we are pulling it out of the ground faster than it takes to replenish, okay? Thousands of years for the biosphere to generate the organic matter consumed by our society in a day. So we're withdrawing it and using it much faster than it's being replenished. That's the big difference between renewable and non-renewable. Fossil fuels are beneficial. Why do we use them so much? They have a high energy content. You get a lot of bang for your buck out of them. So they're more efficient to burn, to ship, and to store. We use fossil fuels for pretty much everything: transportation, manufacturing, heating, cooking, and the big thing that we use is electricity generation. And if you look at this graph, world fossil fuel consumption, okay, billion tons of oil equivalent, right? Most of it is oil, and then coal and natural gas as well. Fossil fuels are not evenly distributed, just like water wasn't evenly distributed. Fresh water in chapter 15. Fossil fuel reserves are not evenly distributed. So again, this gives us haves and have-nots. Like water is a big commodity, right, and can cause tension and stress. Fossil fuel abundance is another one of those sources of stress. So we have the biggest reserve of coal. Venezuela and Saudi Arabia have the biggest reserves of oil sands in Venezuela, and most Russia and Iran have a lot of the natural gas. Russia also has a lot of coal, okay? These countries, Russia, Iran, Saudi Arabia, Venezuela, we're not really close with those countries. We don't really get along with those countries. So that in and of itself provides a lot of tension and a lot of stress on our ability to get these resources. Canada pretty much gets along with everybody. Canada doesn't really fight with us. We share a continent. So that's why we are a major importer of that tar sands oil from Canada. This makes sense. Developed countries consume more fossil fuel than developing countries, okay? Look at this tan. Most of Africa, most of, Southern Asia is in Mexico. The developing world where populations are going up tremendously, but they're still developing on that demographic transition, don't use a whole lot of fossil fuel. United States makes sense. Canada makes sense. Iceland, the Scandinavian countries make sense. Saudi Arabia uses a lot of oil because they have a lot of oil, right? So they have it to use, so they wind up using it. Okay. Typically, in the United States, I'm not going to test you guys on this diagram, but this kind of shows you the where we get our energy from: coal, oil, natural gas, and coal. All right. So from this diagram, all right, there's not quite a bit of the electricity that is the resources that are consumed wind up being lost as heat. All right. So pre-fracking, which we talked about previously, most of the electricity was generated using coal. Now it's using natural gas because of the success of fracking in the United States. Not a whole lot is generated by nuclear and renewables, a much smaller portion than coal and natural gas. So it takes energy to make energy. In order to get fossil fuels out of the ground, in order to build a hydroelectric dam, it takes resources, right? You have to use machinery. You have to create roads, pipelines, waste ponds, storage tanks, all of this stuff, right? So in order to get that energy out, you have to put energy in. We talk about this idea of net energy, is the difference between the energy returned, so the energy you get out, versus what you put in. So net energy equals energy returned minus the energy invested. If you're not going to get, if this number, this net energy is not positive, it doesn't make sense for you to go and utilize that resource, okay? You're not going to make money. You're not going to get anything out of it. That's why nuclear fusion, yes, nuclear fusion is not something that we do. And we're going to talk about that in the next chapter, right? So this number needs to be positive, right? So you can do a ratio, right, rather than net energy. You can do the math to figure out your EROI, your energy returned on investment. You take the amount of energy that's returned divided by the energy invested, and you get a ratio, right? This is important. The EROI goes up, the ratio goes up when the extraction is easier or more efficient, right? You've developed more technology. The resources are easier to get to, whatever, right? So the ratio is going to go up. You're going to get more energy for your investment when these things happen. It's going to drop. The EROI is going to drop when the resources become depleted. There's less there, or it's harder to get at. All right. So here's an example. EROI for conventional oil and natural gas. The way oil, pull it out of a well, natural gas comes out of a well too before fracking and all that other stuff. It dropped from 24 to 1, 24 units of energy for every unit of energy invested in the 1950s, down to 11 to 1 currently, okay? That's why we thought that, that's why Eisenhower invested in the roadways, right? The EROI for oil, which is used to make gasoline, was really high, you know? So it's like, gas is going to be cheap forever. We have no problem. Boy, was he wrong, okay? But again, you make those decisions based on that information that you have at that point. We are using huge amounts of money and mental capital and technology and energy to really push deeper for fossil fuels. So we're drilling deeper into the Gulf of Mexico for oil. We're looking in the Arctic now that the sea ice is melting to get oil out of there. We're using new resources and investing money in the technology to utilize the tar sands, okay? But is that the right thing to do? That's a good question that you guys can think about. So how do fossil fuels form? You have partial decomposition, right? In order to get fossil fuels to form, you have to have partial decomposition. And it's not dinosaurs, okay? So they were formed hundreds of millions of years ago from photosynthetic organisms, right? So you got the ancient swamp, which is terrestrial, and the ancient ocean, which is aquatic. So if we look at how coal formed over here, in like the Mississippian period, hundreds of millions of years ago, there were huge, big swamps, literally from like what is now upstate New York, all the way down through Pennsylvania, into Virginia, West Virginia, Tennessee, where the Appalachian Mountains are, okay? So these swamps, all of the vegetation died, and it fell into the swamp. It started to decompose a little bit, but not completely, because there was just a huge amount of plant matter there. So it started to partially decompose, but heat and pressure and other layers of sediment put on top created the precursor to coal, which is called kerogen. All right. In the aquatic ecosystems, you have these marine plankton, okay, phytoplankton, zooplankton, other organisms. They die. They sink to the sea floor. There's such a huge population of them. They start to decompose a little bit, but they have sediments accumulate over top of them, and more heat and more pressure happens, and you get natural gas and crude oil, right? And typically salt too. Salt forms as a rock around these things. So if you want to be a geologist and you want to work for like ExxonMobil or BP or any of these oil companies, you look for salt deposits, thick salt deposits, because under these thick salt deposits, you're going to have natural gas and crude oil. So this is when they, like Deepwater Horizon in 2010, they were drilled into a deposit like this. So that's oil and natural gas and coal. So coal is what forms in these swamps, right? And that woody organic matter winds up getting compressed into solid carbon structures. So what happens over time and with increasing heat and pressure, moisture content decreases, so you get a harder kind of coal. All right. So the longer the time and the increased heat and pressure, the decreased moisture, the higher the grade of coal. So if it's a higher grade coal, it's got denser carbon content and more energy per unit volume. So anthracite coal is the hardest coal. It's the greatest bang for your buck in terms of coal. And as you move away with less heat, pressure, and less time, you get lower grades of coal, right? Peat, we're going to talk about peat. Where they cut peat out of bogs in like Scotland, and they dry it out. It's really wet. It's not very well decomposed at all. It's really wet. They dry it out and they burn it. It's really smoky and it burns really dirty. So you get cleaner coal burning as you go across to anthracite because you have less moisture. We're going to talk about coal mining in the next unit. They strip mine, they subsurface mine, and they mountaintop removal. Mountaintop removal has become less of a method, but strip mining and subsurface mining are your two primary ways. Spoiler alert, neither of them are great for the environment. So when you pull fossil fuels out of the ground, okay, you can get crude oil. It's unrefined oil that comes out of the ground, typically out of a well. Natural gas is less dense, so it sits on top of the crude oil deposit. It's mostly methane, but some other easily evaporated or volatile hydrocarbons. Petroleum is the overall name we give to these things, crude oil and natural gas. We talked about how they derived from marine plankton in the picture. So these are the oil sands, right? So it's this slurry of sand and clay with bitumen in it. So what they do, they strip mine it, right? They cut the earth away, dig it up, put it in the trucks. The trucks take it to the crusher. They crush it, they break it, they add hot water. Because it's oil-based rather than water-based, the oil rises to the top. The bitumen gets skimmed off and sends that synthetic crude oil, it's mixed with other things, becomes synthetic crude oil and gets sent off to a refinery. All this, the hot water slurry that's left behind has to be put somewhere, okay? So this becomes those surface impoundments full of toxic chemicals, because it's not just water that's in there. There are chemicals to help physically separate the bitumen from the sand and the clay, right? So that's the strip mining method. Definitely not an environmentally friendly, ecologically aware method of extraction, okay? A little bit better way is this idea of steam extraction, really similar to fracking. They dig these wells, right? These wells, and they shoot hot water, steam, and solvents down into the bitumen deposit. That melts the bitumen deposit, and then they suck it back up. Again, you don't know what solvents are in there besides water. If it was just hot water, that would be one thing. Those solvents could contaminate drinking water. That comes up. And then the same processing happens. They remove the bitumen from the rest of the material, the liquids and the steam, and that liquid and steam becomes surface water toxic tailings. We just talked about that. Methane hydrate is something that they're talking about now that we have a lot of ice melting at the poles. It's solid molecules of methane embedded in a crystal lattice of water molecules. So it's found in sediment in the Arctic and ocean floors. So there's a lot of concern about that, because if you disturb that, are you going to be able to capture all of that methane, or is it going to wind up heading up into the atmosphere? Methane is one of the big contributors to global warming. Okay, so we're a little hesitant to mess with that one. Okay, so it's all about the money. I don't know if you guys have figured this out yet, but it's always all about the money when it comes to these kinds of things. So whether or not we extract a material determines on how much money you're going to make. So if you look at this, the fuels that you can physically get to, you have the technology to get to, are called technologically recoverable portions. The things that you have the technology to get to. Okay. The economically recoverable portion of the fuel depends on how much it costs to take it out and what you're going to get for it, right? You might be able to technologically get to it, but it might not be worth it because of the cost of getting to it. Okay. If it is technologically and economically recoverable, we say that those reserves are proven recoverable reserves. Okay. Technology has gotten a lot better. Costs have gone up to make more of these fossil fuel deposits proven recoverable, rather than, the tar sands when I was in college were not proven recoverable. They weren't economically recoverable, and they weren't technologically recoverable. I think the economically recoverable part happened first. There was money in it, and then they developed the technology to make it happen. You can refine crude oil based on boiling point. So you heat up the crude oil, and depending on the boiling temperature, you get different products, right? Fuel oil, gasoline, it stratifies. And if you drive to Newark Airport or Philadelphia Airport, frankly, you see these distillation columns on the side of the road off the highway. And that's where oil refining takes place. What gets separated out gets used in a whole bunch of different processes. Jet fuel, gasoline, liquefied petroleum gases, propane, that kind of thing. Industrialization determines, and then therefore level of development determines how much fossil fuels a country will wind up using. Okay. And each fossil fuel has its own mix of uses. So coal, right? China produces almost half and uses a little bit more than half, okay? That's mostly for electricity generation. Oil is used for gasoline and that kind of a thing. Natural gas, we produce the most, and it turns out we use the most. When we get to, as we're talking about in this unit, the energy conversions and that kind of a thing, when we generate electricity, okay, this whole part of the slide varies, okay? So in order to generate electricity, you need some kind of method to turn a turbine, to run a generator, to generate electricity, okay? What happens before turning the turbine to generate electricity varies, okay? So this is a coal-fired power plant. What do? They dump coal into a pulverizer, right, to make it really fine. They blow it into a furnace where it gets hot, right? The furnace burns the coal, which heats water, Okay, so it creates steam. The steam turns the turbine, which generates the electricity. So in a coal-fired power plant, in really any fossil fuel-fired power plant, that was hard to say, whatever you're burning creates steam, which turns a turbine, which generates electricity. Okay, that water is in a loop, right? So this water that was steam to turn the turbine to generate electricity has to cool down. Okay, so there's cool water that runs through this condenser, which allows this steam to condense back into water. So this condenser loop pulls the heat out of this water to help it turn back into, of this steam, to help it turn back into water to go through this process again, right? So the water runs through the condenser, brings the heat out of this loop, the turbine loop, and it comes out of the cooling tower. So when you see these big giant cooling towers near a power plant, it's not chemicals that are coming through, okay? It's typically heat from that water before they cool it and put it back into a body of water, the ocean, a river, whatever. All right, so there's material that's produced as a result of that, particulate matter that goes up into the air, plus ash, okay? The air gets filtered, right, and cleaned so that those pollutants do not make their way into the atmosphere. So they get cleaned up. We're going to talk about, we've actually already talked about that, scrubbers, the idea of scrubbers, okay? And the material that gets filtered out and the ash then gets taken to a hazardous waste landfill. So there's actual physical waste that is produced rather than just the air pollution and potential thermal pollution from water. We use petroleum products everywhere, petroleum-based products, plastic, vinyl, anything synthetic is going to wind up being part of petroleum use. Waxes that are on your fruit, any of it. Asphalt on your driveway or on the road. So we are, Captain Obvious, we are not using fossil fuels sustainably because it takes so long for them to regenerate, okay? So people who do this for a living, they're analysts, they can look at the reserves to production ratio and figure out how much of these fossil fuels are there compared to how fast we're pulling it out. And we can calculate how many years we have left of a particular resource. So oil, we have 53 years of oil remaining. I may not be around then. Chances are you guys are going to be. So natural gas, our ratio means that it's going to last about 54 more years. So not that much longer than oil. And coal's about double that, 110 years, based on those ratios. So we are running out of fossil fuels. That amount of time left could change if we change the demand. So if we reduce demand, it's going to last longer. If we increase production, it's going to last longer. Or if we have changes in the levels of our reserve, okay? So if we find a new deposit, then the source might last longer. So fracking is allowing us to get more oil that's confined in shale that we weren't able to get before. Eventually, we're going to reach a peak, and then we're going to decline when it comes to fossil fuel extraction, or really anything non-renewable. If it holds steady, if our demand holds steady or increases when this happens, we're going to wind up with shortages. And they call it peak oil because it's likely to happen at some point. So there was a Shell oil geologist that predicted that we would hit peak oil in 1970. And we did, but then we discovered new resources. So production has been able to go back up. So we have a life preserver because we've increased our technology and extended our reach for those fossil fuels. What's going to replace it? We're going to hit it. what's going to happen? Where are we going to go from there? So we've got conventional oil, but now we're looking at all of this unconventional oil. That's really kind of helped us over this peak conventional oil potential issue. We'll talk about what we think could replace it in the next chapters. So what are we doing? We are extending our reach for fossil fuels by doing a bunch of things. Mountaintop mining, doing something called secondary extraction, fracking, which we talked about, digging in deeper or drilling in deeper water, and getting accessing some things that we didn't think were potential fossil fuel sources. They increase production, so we have more supply, but EROI drops. We have to invest more energy in order to get that energy. Okay? We're causing more pollution, and we're also increasing climate change. So mountaintop removal. This is the first time you're going to hear about it. You're going to hear about it again when we hit chapter 23 in the next unit. You literally rip the entire mountaintop off, okay, to get to the coal. It's like, chopping the top off your hedges, only you're chopping trees, topsoil, and rock, right? You have so much rock and soil erosion, okay? This is all of this, when it rains, all of this soil and sediment is going to run down into these creeks and down into the lower lying areas, right? This is what the natural environment looks like, is supposed to look like around it. Looks completely different. And the idea of secondary extraction, you stretch a little further in an oil or gas well. You don't get all of it, so you go back in with solvents, water, or steam to pull that remaining oil or gas out. It's a lot more expensive because you have to invest in these solvents and in the drilling gear. But it does get you the resource. Directional drilling, like they do with fracking, you can drill down vertically and then drill down horizontally. So then what you can do is you can allow that horizontal drilling. You can even drill in a radius, right? So you can make a circle around that vertical drill to get more material without constructing additional drill pads. To construct a drill pad is really expensive. So if you have the pre-existing drill pad and you can just stretch your reach out a little bit, it's economically better. We talked a lot about fracking, where you put chemically treated water and steam down into the ground to crack open rocks, and then oil and natural gas come up with it. We talked about the water resource issues with that. And really, this is a fracking rig behind somebody's house. It causes air pollution, it causes water pollution, is really not a good place to want to live. Natural gas, because of fracking, has decreased, production has increased tremendously, making it a much cheaper alternative to coal when it comes to generating electricity. So that is why most of the United States most states in the United States, including New Jersey, use natural gas to generate electricity. We're drilling further offshore. We're in really deep waters, and we're going to talk a little bit more about that when we talk about our key points. We're going to talk about the Deepwater Horizon oil spill and what happened. Our technology was ahead of our ability to deal with the accidents. The Deepwater Horizon well spilled oil into the Gulf of Mexico for months. So they decided to just hold off because of the environmental damage that happened as a result. Because the Arctic sea ice is melting, it has exposed a lot of shelf areas to offshore drilling, but it's still not, just because the sea ice is melting doesn't mean it's a good place to go drilling. It's cold, it's windy, there's ice flows, chunks of ice around everywhere. It makes it difficult to drill, and the likelihood of an accident is really high up there. Currently, we are not drilling in the Arctic National Wildlife Refuge, but there's a lot of conversation about doing that and opening that up. Methane hydrate, Japan has attempted to extract it, but they don't do much with it because of, like I said, the issues with high methane release. Oil shale has a really low EROI, 4-to-1 or 1.1-to-1. So it's really not, it's an alternative, but it's not a really solid alternative to conventional oil. So there's the oil sands area. It has a huge impact on landscapes and natural habitats. Talk about habitat fragmentation, talk about surface water pollution. Okay. If you are a coal miner, okay, if you are a subsurface miner, you have a lot of susceptibility to lung diseases because you're inhaling coal dust. Black lung disease is a disease that was very common in the coal miners in Appalachia from the 1800s even up to today. If the mine collapses, that's a hazard. Okay. When you do the mountaintop removal or the strip mining for coal or oil sands, you wind up losing a lot of soil. Acid mine drainage happens when you have these sulfide minerals that were below the surface that are exposed to rock, that were exposed when they did the mining to oxygen and rainwater. It produces sulfuric acid, which drops the pH of the water, and then organisms won't be able to survive. And then habitat loss. When you have mountaintop removal or strip mining, even if there's a law that we're going to talk about when we get to chapter 23 that talks about having to put things back the way you found them. You can't put it back exactly the way you found it. So you're going to lose habitat. And oil drilling, the main impacts of oil drilling are the infrastructure needed to support it, the pipelines and the refineries and the trucks and all of that. So fracking, we are still learning about the issues related to fracking. You can leak fracking fluids from these drilling shafts as the rocks crack open into nearby aquifers. Methane may not escape into the tube. It might make its way into aquifers. Methane in an aquifer makes the water burn, which it's not supposed to do. You can get air pollution as as the methane comes up through the well. It doesn't all come up through the tube, so it can escape into the air. And the volatile organic compounds, or VOCs, that we talked about before, can be released through the fracking fluids, as well as when they're released into the air if it doesn't make its way back through the tube. You can have that injected water, that goes down, contaminated by things that are down in the rock. And fracking has also been known to open up faults and natural cracks in the rock and cause minor earthquakes. They're having a lot of those in West Texas and the Oklahoma Panhandle, western Oklahoma. And if we took the look at that picture from Alberta, the oil sands are really ecologically damaging because you get rid of all the forests, you clear the surface, you strip mine the surface, you use a ton of water to pull that bitumen out, and then you have a whole lot of wastewater left behind. So this is the impact of the oil drilling in the Arctic National Wildlife Refuge. It will definitely have a lot of issues and a lot of impact for, native species, right? The polar bears and the caribou and native people. So another downside of fossil fuels is that they can leak. During transport and storage, there were train derailments. Oil and coal are transported by train. You can have natural gas pipelines that explode, or there are issues with those pipelines that cause natural gas to escape into the air, which can cause breathing problems. Methane can also escape during oil drilling because there's not a catchment method for it. Pipelines, because they're metallic, are subject to corrosion, vandalism, and equipment malfunction. The emergency shutoff systems failed in Deepwater Horizon, so it exploded and then it sank because they couldn't turn it off for 3 months. They couldn't figure out how to stop it, and we'll talk more about that in the key points. Some impacts of Deepwater Horizon. Native birds were coated in oil. These are like sugar beaches. The beaches in the Florida Panhandle are white and really fine sand. They were completely covered with oil, and people were out there scraping it and cleaning it. We talked about the Exxon Valdez, and we also talked about the fact that most of the oil pollution entering the oceans is non-point source, right? It's not like tankers or oil rigs that are spilling millions of barrels of oil into the water. It's stuff that's non-point source that it's a lot harder to regulate. So one thing that we're talking about using if we need to burn coal is to use clean coal technology. So you reduce the pollutants that come out of coal. You use minerals in the burning process that are going to absorb the bad chemicals in coal, like sulfur dioxide, which we called SOx, right? Or the NOx, the nitrogen oxides. And you can also dry it or convert it into a cleaner synthesis gas called syngas to make it cleaner burning. So there's clean coal technology. Again, EROI, you got to invest a lot more in it. So burning fossil fuels, we talked about this when we talked about the carbon cycle. Burning fossil fuels alters the carbon cycle. We're pulling long-term reservoirs of carbon out of the geosphere, and we're shifting it into the atmosphere in the form of carbon dioxide. Okay, and the increase in carbon dioxide as a greenhouse gas is the biggest downside of fossil fuel use. Fossil fuel use has increased tremendously in the last 200 years, mostly due to the Industrial Revolution. So, what can that do to humans? We talked about all the environmental impacts. What can that do to me? Okay, when you burn coal, mercury is a component in coal. That mercury can go up, can vaporize into the atmosphere and fall into the water or onto the land, which will biomagnify in food chains and then biomagnify in us, okay, if we eat those organisms. Benzene and toluene are known carcinogenic hydrocarbons that come out of, that are released as the result of burning gasoline. Hydrogen sulfide evaporates from crude oil in that refining process. Vehicles and power plants release SOx and NOx, which we learned wind up causing acid precipitation. Okay, so when we burn these fossil fuels, we release SOx and NOx, which will combine with the water in the atmosphere and form sulfuric acid and nitric acid, which are key components in acid precipitation. So I was watching a 60 Minutes episode about carbon capture and storage. So a lot of the oil companies, right, the petroleum industry is looking to do this. So they capture carbon dioxide, they convert it from a gas to a liquid, and then they store it underground or in the ocean. Underground, they store it in a geologically stable rock formation. And I have a lot of hesitancy about this method because I know, you will know, that the lithosphere is rapidly changing. So it may not be an issue in our lifetime, but it could be an issue in our children's lifetime or our grandchildren's lifetime, that these geologically stable rock formations may no longer be geologically stable. We don't know if it's going to stay under there. We could contaminate groundwater supplies, and it is very energy intensive and adds to the decrease in coal's EROI. So we wind up paying at some level for all of these things related to fossil fuels. We don't pay for it at the pump, right? If we had to incorporate the cost of all of these things into what we pay for a gallon of gas at the pump, we would not buy gasoline, okay? So the medical expenses for the workers, for those involved in transport and refining and manufacturing, the environmental cleanup, right? We don't have to pay for, we didn't have to pay at the pump for what British Petroleum, BP, did in the Gulf of Mexico. And any long-term damage from climate change, we don't have to pay that. Why? Because they've been kept artificially, the cost of that, the money we pay at the pump has been kept artificially expensive because of government subsidies. The government pays the fossil fuel industry to keep prices low, and tax breaks for extraction companies. They don't get taxed as much because they are providing fossil fuels. Okay? If these subsidies and tax breaks and incentives disappeared and we added these external costs into what we pay at the pump, we would not be using gasoline. Okay? So locally, right, you've got high-paying jobs when a fracking well comes into town, right, or a coal mine opens, right? There's jobs, and there's a lot of economic activity. There's people in town that want to shop and buy houses and do all this stuff. But the problem is these are non-renewable resources. So when that well or mine runs dry, the people are going to go. The jobs are going to go. And the people that live there that are left behind are going to have to deal with the consequences, right? So this is the idea of methane in the water. That's a match. That's a faucet, and her water is on fire. Like, that's not supposed to happen, okay? The Keystone XL pipeline was a potential situation or circumstance where the government could have instituted something called eminent domain, okay? It's a policy where courts can set aside private property rights if the project has been deemed beneficial for the general populace, right? So we had the Penn East pipeline trying to come through, and we fought it for a really, really, really long time. And, you know, my dad's, the pipeline was going to go through the right-of-way, like where the power lines and stuff go. And that right-of-way, my dad's, part of my dad's property was within the easement of that right-of-way. And Penn East was going to come in and eminent domain a portion of my dad's property. And fortunately enough, environmental activist organizations fought it, so that way it doesn't exist anymore. But, you know, we finally defeated Penn East. But if the government or the court system deems the project to be useful to the general populace, they can come and take your land. So why did we move towards Canada? Why did we start to get our oil from the tar sands in Alberta, Canada? If we look back one of our previous slides, most of the oil and coal reserves, oil in particular, are in countries that really aren't super friendly with us. Venezuela, Iran, Saudi Arabia, okay? We get involved in places that we shouldn't necessarily be involved in because there's some resource there for us. The Gulf War happened in the 90s because of the fossil fuels, how close everything was to the fossil fuel industry. So we had a need in the United States to protect that resource, protect those reserves. So that's why we went. That gives the fact that fossil fuels aren't evenly distributed, gives seller nations, nations with higher reserves, more control and more power over energy prices, especially as the reserves go down. So in 1973, there was an organization called OPEC, Organization of Petroleum Exporting Countries, decided that they were not going to sell oil to the United States. So it created an energy crisis. You can ask anybody who was around in 1973, grandparents, mom and dad, if they're that old, you would have to wait in line to get gas, okay? And then if you had to wait in line to get gas, they might run out of gas right before you got there. So it was a big, big issue, okay? And we've had prices change and fluctuate over time based on how friendly these seller nations are to us. So the fact that OPEC stopped selling oil to us gave us this indication, okay, maybe we need to look somewhere else. So that's why we moved to looking at Canada. Okay, and there's what that says. So how can we deal with the fact that we're running lower on fossil fuels? Okay, so we can look at energy efficiency versus energy conservation. So energy efficiency is when you decrease your input, you use less energy to get the same amount of energy out. So it's typically improved technology. You look at Energy Star appliances, LED light bulbs, that kind of thing. You're using less energy, but you're getting the same output, okay? Energy conservation is being more mindful of your energy use, making good choices, right? Turning off the water when you brush your teeth, turning out the lights when you leave a room, etc. Okay? We use a lot more energy than other nations, so we could probably reduce our consumption without really suffering too much. We are going to skip that. This idea of cogeneration is cool. So cogeneration is where you take excess heat produced during electricity generation and use it to heat nearby workplaces or homes. I did an APES Summer Institute at Rutgers, and they took us to one of the power plants on campus in New Brunswick, and it was a cogeneration plant. So they produced electricity. They burned natural gas to to create steam, to turn the turbine to generate electricity. And then that steam they had a network of pipes to the labs and dorms not too far from the power plant, and they ran the steam through those pipes to then heat water to power the furnace, and the hot water heaters. Okay, so that's the idea of using that energy in two ways. You can also improve design. Right, these three houses that are green are losing a lot of heat. This one in the middle has better insulation, so it's retaining heat better. We talked about improving technology, right? Consumer electronics, Energy Star using better bulbs, okay? And we've actually decreased our electricity use since 2010, typically as a result of using these kinds of bulbs. There's the Energy Star label guide, how much it's going to cost you a year. You can choose. These are on all of the appliances that you see at Home Depot or Lowe's or wherever you go to shop for appliances. So this is not a decision that you can necessarily make now, but maybe you can say to your parents, hey guys, if we need a new refrigerator, let's look at this, and you can explain that to them. When you go down the line, when you get out into the world and making decisions like that for your house, you can take this into consideration. After the OPEC embargo in the 70s, when OPEC stopped selling us oil, we started to increase CAF standards, so corporate average fuel efficiency, right? The average fuel efficiency of these vehicles based on different kinds of vehicles, right? So cars, CAF, right? Fuel efficiency has gone up considerably. I think the most recent CAF standard I saw was 32 miles a gallon for regular cars. Okay, trucks it's a little lower, but if you take the average, we're getting a lot better. Don't worry about that. How are we going to solve the problem? Stretching our reach for fossil fuels is not necessarily the best way. It's a mix. It's a combination of energy efficiency and conservation that is going to allow us to do the best we can with the fossil fuels that we have. But there are other technologies that exist that might be useful to us, and we will talk about those in the next chapter.